since it went over S, P, and D, that F must be in the next section, but it wasn't. I don't know why they left out F. So this is a drawing of an F orbital. So they're not like X, Y, and Z like the P orbitals are, but they're sort of similar in that they're on different axes. So 3 of them look kind of like P orbitals, except they have 2 donut rings around them. So they're like a figure 8 with 2 donut rings. And so there are 3 of those. And then there are 4. This is a really bad drawing of this, but it should look more like 2 4-leaf clovers stuck together. Or if you took 8 balloons and you held them by the end where you blow in the air and you tied them in a knot, you held all 8 balloons together, that's the kind of shape that you would get. And so there are 3 of those. And there's one other one that I must have missed, because there are 7 F orbitals. So either there were 4 of these, or there must have been another one like at the top or something. But that's generally what F orbitals look like. All right. And so one thing to note, when we, like all 4 of those, all 4 of those orbitals, like the, okay, yeah, so there must have been like another one of those that looked like a 4-leaf clover or something like that. Somehow I missed the 7th orbital, but if you go to Google and you type in shape of F orbitals, it'll pop up lots of images that you can look at there, and you can see the 7th one that somehow I missed the 7th one. So today what we're going to do is we're going to figure out where it is that electrons reside around a nucleus. So we went over N, and N is the principal quantum number that gives you the energy level. So the lower the N, the lower the energy. So N equals 1 has less energy than N equals 9. So then we went over L, which was giving us the shape. And so that's S, P, D, and F, or 0, 1, 2, and 3. So ignore the little chart at the bottom for right now. That's not telling you about L. It's telling you about the number of orbitals. So when L is 0, that's an S orbital. When L is 1, it's a P. L equals 2 is a D. And L equals 3 is an F orbital. And it's important to note that each of these lines out to the right can hold 2 electrons, 1 up and 1 down. So an S orbital is just going to be able to hold 2 electrons. It just has 1 orbital. And the P's have the PX, PY, and PZ. And so they can hold 2 electrons per dash. The D's have 5 orbitals, so they can hold 10 electrons. And the F's have 14, not 14, they have 7 orbitals, so they can hold 14 electrons. And there's an easy way to remember that. As long as you can remember S, P, D, F. Hang on a second, there's a phone ringing. It'll be done here in just a second. A little free entertainment for you in the background. Okay, so if you remember SPDF, yeah, please hold. SPDF, the number of orbitals is just the odd numbers, just counting odd numbers. So it's 1, 3, 5, 7. So the S orbital has the S subshell has 1 orbital. The P subshell has 3 orbitals. The D has 5 and the F has 7. And you just have to remember that each one of those orbitals can hold 2 electrons. All right, and then we have the Aufbau principle. The Aufbau principle just says that when the electrons go into the atom, they're going to fill up the lowest energy orbitals first before they start filling up the other ones. So it would go 1s and fill those up, and then it would go 2s and fill those up. It wouldn't skip 1s and go 2s and then like 9g or something like that. They can get in that arrangement, but that's just when the electrons are excited. And in general, when we're doing electron configurations, we're doing that of the ground state, which means they'll be in the lowest energy. So let's fill up the lower levels first and kind of build on that. And then the electron configuration is just a written representation to tell how the electrons are arranged in an atom. So it'll be written something like 1s2, 2s2, and I'll kind of show you what that means there. All right, so another thing we talked about last time was the principal quantum number. We'll be doing electron configurations on the test. Yes, definitely we will. And to use the diagram for the Aufbau principle with the diagonal lines? Yes, I do. There's another way also that's easy that you can use the periodic table. So there are two methods. There's one with the diagonal lines and there's one with the periodic table. And I'll show you both methods today. So the principal quantum number is n, and it's also called the energy level. So sometimes they say, what's the energy level of, and then that's whatever the n level is. So when you write an electron configuration, the first thing you have to do is figure out how many electrons are in the atom or in the ion. So if you have a neutral atom, the number of protons is going to be equal to the number of electrons. As protons are positive, electrons are negative, and they have to equal out in order to be neutral. In an ion, that's going to be a charged atom. It's either a positive charge, that's called a cation, or a negative charge, and that's called an anion. And that's going to be where they either gain electrons or lose electrons, forcing the atom to be charged. And then it's called an ion. To figure out the number of electrons is the atomic number, which is the number of protons, minus the charge. And so that's the number of electrons. And I do some examples later in the notes, and I'll show you that. Oh, actually, here are the examples. Go me. I'm just kidding. All right. So with sodium, if you look on the periodic table, you'll see its atomic number 11, which means it has 11 protons. And the charge you can see right there with the plus. If there's no number next to the plus, that just means plus 1. If there was a number like a 2 next to it, that would just mean plus 2. That would just be the charge. Yeah, they should be under notes. Are they not available under notes? They are? Okay, yeah. So if you go to D2L and you click on content and then you click on notes, you'll be able to find these notes that I'm going over right now are on D2L. They weren't this morning, but they are now. All right, so if you take the 11 protons and subtract the charge, which is plus 1, it's 11 minus positive 1, and that's 10. So that's 10 electrons. You're welcome. Are all Chapter 3's notes in D2L? Everything except for what we did on Monday, and I just have to figure out where I put those notes. I'm pretty sure they're on D2L somewhere, but I don't know where I put them. So that's going to take a little bit of hunting for me. Okay, so below the little 11 minus 1 equals 10 electrons, you'll see that I drew out in red, you'll see all those little pluses. Those represent the protons. So I wrote 11 pluses. And above that, I wrote the number of electrons. And there were 10 electrons. And so you notice every time I have a plus and a minus, I crossed it out because those would neutralize each other. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sets that neutralize each other. and then I circled the leftover proton, and that's why it's positive. So it has a positive charge, and a lot of people mistake it and think that that means there's an added electron, but what it means is that one of the electrons has been ripped away and left part of the nucleus bare, which gives it a charge. An example, so that was a cation, sodium, because it's positive, and an anion is below that, that's fluorine. I'll bring it up to the top of the page. It's atomic number 9, and you can see that it has a charge of -1. So here is 9, which is the atomic number, minus, and I put in parentheses the charge, -1, and when you have minus a minus, that becomes a plus. So beside that, I put 9 plus 1, and that's 10 electrons. And below that, I did the same thing with pluses. So that was 9 pluses because we had 9 electrons, not electrons, 9 protons. And above that, I put my 10 electrons. And I have 9 cases where they cancel each other out and 1 leftover electron. And that 1 leftover electron is what gives it the -1 charge. If I had 2 leftover electrons, that'd be a -2 charge. All right, and then so we're just kind of going over the concepts first and before I show you how to do it, just so you understand more about it when we get to it. So it may seem a little like it's not quite put together in your mind yet, but we're getting there, so don't stress over that. The Pauli exclusion principle, and you need to memorize this one. This one's like on final, it'll be on tests, all over the place. So you want to know the Pauli exclusion principle. Yes, the atomic number minus the charge will tell you if it's an anion or cation. So if it's positive charge, cation. If it's negative charge, anion. All right, and so with Pauli exclusion principle, it's just telling you that you can't put 2 spin-up electrons in one orbital. They have to be 1 up and 1 down. So if you looked at the bottom where it's in black, it says spin paired. So the electrons have to be spin paired. What that means is you have to have the m sub s, which is the quantum number ms, either it has to be a combination of +1 and -1 if there are 2 in that orbital. Sometimes you'll have an orbital with just 1, and that's okay. But if you have 2, they have to be 1 up and 1 down. So I've drawn to the right at the bottom, there's a line, and then there are 2 half arrows. Those half arrows represent electrons, and the one that's pointing up is the +1/2, and the one that's pointing down is the -1/2. All right, so now we get into just an example of what is an electron configuration. So if you look on the periodic table, you'll see hydrogen is atomic number 1, and it's neutral in this case right here. So we have 1 electron and 1 proton. And the first level that you'll find is always the 1s level. So I drew the 1s level, and I put the 1 electron in it. And just traditionally, it's normal to put the +1/2 in first, so the up arrow goes in first, and the down arrow goes in next. I don't know that it's technically wrong if you put the down arrow in first. It's just people just, out of convention, they just put the up arrow first there. All right, and then if you look below that in color, you'll see I have written 1s1. The first number, which is in blue, is the N level. And the second letter, well, the first letter, which is the second character there, is in orange, and that's the L. So L must equal 0 here because it's an S. And every time L is 0, that means S orbital. And then there's another one that's a superscript, and that superscript tells you how many electrons are in that particular subshell. Below that is the electron configuration for helium. Helium has 2 electrons, And I'll get into more detail about these in a couple of pages. Helium has 2 electrons. So the first orbital is the 1s. So I drew the line and the up arrow and the down arrow. The part where I draw the line and the arrows, that's called an orbital diagram. And then over to the left where I write 1s2, that's an electron configuration. A lot of times it's easiest to write out the orbital diagram first and then write down the electron configuration. No, actually we're going to use the Aufbau principle for N. So there's a method to that, but we'll get to that in a page or two to figure out what N is. That's a good question though. So the atomic number, it just kind of helps to figure out how many electrons there are. So you have to do atomic number minus the charge. And that's the only thing we really use the atomic number for in here, that and to identify what element it is. So if they said, well, you have an atom, its atomic number is 11, it has a +1 charge, what is it? Then you say, oh, that's sodium, because you find the 11 protons there. Why was it both arrows instead of 1? That's a good question. That's actually important. Okay, so if you look at the top, helium has 1 electron, so it got 1 arrow. So each arrow represents 1 electron. Helium has 2 electrons, so it has 2 arrows, 1 up and 1 down. And so its electron configuration is 1s2. And you see the only difference is that one of them has 1 electron as a subscript, not subscript, superscript, or exponent. And then the second one has 2 as a superscript or exponent. And we'll get way deeper into that in a couple of pages. That's just to kind of let you know what we're headed toward. The next one that you have to know is Hund's rule. And Hund's rule says that if energy levels are degenerate means they're the exact same energy. So, for example, if you had a p orbital or a p subshell, there are 3 orbitals, the px, py, and pz, and they're all in line with each other. So they're all equal in energy. That means they're degenerate. So if you have degenerate orbitals, you have to put 1 electron in each one of the orbitals first before you start pairing them up. And the reason is because electrons naturally repel each other because they're negative. But once you've maximized, or not maximized, once you've minimized the repulsion by putting an electron in each orbital, then you have to come back and start doubling up because the magnetic properties will then attract them to each other. Exactly, you do have to fill the bus before you double up. That is excellent. So what they're saying basically, what Anna's saying is that if you were to imagine it like the orbitals being a bus, normally when you get on a bus, let's say a school bus to go to school, a lot of times people will just put 1 person per seat until all of the seats have 1 person in it, and then they start putting a second person in there. Because people like to be, if they don't know each other, they tend to like to be as far away from each other as they can until at least they get to know each other. Now, that's not everybody, obviously. Some people are not like that. Spencer, what can I ask? What do you have a question with?
Hello, can you hear me?
Hi, Spencer. Yeah.
All right, so I'm having a little bit of trouble understanding this because if you scroll up a little bit,
Sure.
To I think the prior page or early up here. Okay, there you are. So
okay.
You were I'm not understanding. So you said up there, I believe that's hydrogen. Over towards the right, there's 1 arrow up that shows that it's positive. Then you have an additional one down below that says there's positive and negative. So
yes,
there seems to be a discrepancy to me because you said before that you need to place 1 in, I think that that individual shell, and then you place another in that shell. Am I getting that correct? Right? Each electron in the 1s shell?
That is actually correct. So the one at the top is helium, not helium, is hydrogen. Hydrogen has one electron. So when
Okay.
you have the orbital, you can just put one electron in it. And then below that is helium, which might not be all that clear to see because it's kind of hidden in all the stuff there. So helium has two electrons, and the s orbital, the s subshell only has one orbital. So you have to fill up the whole orbital before you can go to the next level. So the next level would be like 2s.
Okay,
So-
so I should have been a bit more clear about that. I should have just said helium rather than hydrogen. Scroll
No, that's
down a little
okay.
bit.
Sure.
So for helium, it says that you have two electrons in the 1s shell, but now you're saying that what was it? Anna said that you have to fill the bus before the people double up, but for helium specifically, I guess this might be a bad example, right? I don't
Actually,
understand what you mean.
Okay, no, that makes sense. So with helium, that's going to be the lowest level, and
Okay.
there's not another level that's equal to it. So there's not a degenerate level that's equal to 1s. So you have to fill up the 1s first, and then you go to the second level, and then the next level. So the third level is going to be a p orbital, and you'll have three orbitals. It'll be a p. Well, here, let me just draw it I'll draw it on the board real quick.
Okay, so then a helium wouldn't actually be the best example. What about something like carbon, right? Because
Yeah,
that should
carbon
have.
would be a better example.
Okay, so then we might be able to use carbon for this.
Yeah, let's do sodium because I can remember the number of protons is 11. So then you're going to have 1s. Well, yeah, 1s2, 2s, 2, 2p, 6, and then 3s, 1. Okay. So when we do the orbital diagram, S's have one blank. And then, so that's the 1s. And this is the 2s. And then where you have the 2p, that's going to have three blanks. So that's p. This is going to be the px, the py, and the pz. Just letting you know.
So for P subshells, you would fill up X, Y, Z, then the second one in X, and then the second one in Y, and then the second one in Z. Does that make more sense?
Yes,
would that be a little bit more correct? Okay,
that
then that
correct.
answers my question. All right,
Okay.
thank you very much.
You're welcome. And I'll just fill these in for anybody else. Okay. So the Pauli exclusion principle says we have to do it from lowest to highest. So starting with the 1s, we do 1s and then 2s, and then we do up, up, up. The reason is because these are all 2p orbitals. So you have to put one in each orbital before you start to double up, and that's Hund's rule. So now we're going to go down. At this point, if you count the arrows, you'll see there are 10 arrows, and we have 11 electrons, so we just got to put one more. So that's the orbital diagram for sodium. And I'll show you how to figure out what levels they are in just a second. Erin, did you have a question? All right. So this is one of the ways that you can figure out the orbital level. Let's see.
Professor,
okay.
I can't quite see what's on screen. Maybe I'm just unable to see it properly, but nothing's showing up for me.
Let me click stop, and then I'll try to share it again. Can you see it now?
Absolutely not. I have no idea why that's so strange.
That is strange. Can everybody else see it?
Yeah, everyone
Yeah, you may
can.
have to log off and then log back on. Sometimes it just gets weird like that. All right, so with the Aufbau principle tells you that you have to fill these in order of energy, but they don't always go 1, 2, 3, 4, 5. Sometimes they get kind of screwy. If you look to the right, you'll see it says 1s, 2s, 2p, 3s, 3p, 4s, and then you would think it'd be 4p, but no, it's 3d. So that's a little weird. And then 4p, 5s, and then 4d. That's weird again. And then 5p and then 6s. Every time you come to a d orbital, it's going to be one less than the one you just filled up. And then if you end up in the f orbitals, that'll be 2 less, but we don't usually get too far into the f orbitals. So let me show you how to make this diagram. And then I'll show you toward the end how to use the periodic table. And you wouldn't have to use the diagram, but I like the diagram. I'm used to it, and this is the first way I learned it, and I like drawing the arrows, I guess. Okay, so to draw this, first you start with the 1s, and then you just go down till you get to about 7s. So 1s, 2s, 3s, 4s, 5s, 6s, 7s. And then you go to the next column and you skip 1, and then you write 2p. And then 3p, 4p, 5p, 6p, 7p. And then you go up to the top of the next column and skip a second one. And then 3d, 4d, 5d, 6d, 7d. And then this time you're going to skip 1, 2, 3 rows in the last column. And then write 4f, 5f, 6s, and 7s. And you can see kind of what we're doing here is just, it goes S, P, D, F. And then column 1 is everything. Column 2 is missing 1 row. Column 3 is missing 2 rows. Column 4 is missing 3 rows. And then you draw arrows from the right down to the left. Yeah, they are satisfying. So you draw them from the right to the left, so they go diagonally down to the left of the paper. So you do 1s, and then you come back, you do 2s, and then you come back up, and then this time when you draw the arrow, if you draw it straight, it's going to catch 2 of them. And the next one you draw straight, and it catches 2. And then it starts to get a little bigger, and you draw the arrow straight, and it catches 3, and then 3, and then catches 4 of them, and so forth. If I had made the diagram bigger, the arrows at the bottom probably would have caught more stuff, like the one that only has 6S and 7D in it might have had more stuff. But generally, we don't have to get to the 6F level. So if you look to the right where I have the word Aufbau principle in brown, the letters and the numbers follow the arrows starting from top to bottom. So the first arrow crosses 1S, so in brown I wrote 1S. The next arrow crosses 2S, so that's the one I wrote next. And then the arrow crosses the 2P first, so I wrote that. And then the 3S, which is next, so I wrote that. And so you just follow the arrows all the way down, starting from the top down to the bottom. 7F does have an arrow, but really to catch all of the levels that would be accompanied with the 7S, I'd have had to make the diagram even bigger. But since we don't usually go much below the 4F most of the time, I didn't bother making the rest of the... I didn't make the diagram extra big, if that makes sense. Okay. And then in black, I wrote some orbitals are lower in energy than expected. So, like the 3D is lower in energy, the 4S is lower in energy than the 3D. And you would think that since 3 versus 4, that 3 would be lower, but it's not. And I'll kind of get into why not in a couple minutes. So I started sort of showing you how to do orbital diagrams here. Can you do one of those? Yeah, I do have an example that goes to 3D, and either on this page or maybe in a couple of pages, but I do have one of those. So with oxygen, oxygen usually makes a -2 charge, so oxygen 2 minus. So its its proton number or atomic number is 8. And you subtract the charge, which is -2. So 8 minus -2 is 8 plus 2, which is 10 electrons. So we're going to start with the first arrow at the top of the page. And I'm going to write down one S, and I know the S's have one blank, so I'm going to write one blank above it. The next arrow crosses 2S, so I write down 2S, and I draw one blank because S's have one blank. When do you know